And
I
then,
can see that perfectly. Thank you, Stefan.
okay, perfect. All right. It's a pleasure to be here. Like I just said, more than 100 people willing to spend their lunchtime listening to some information about Slab track system. I really appreciate the enthusiasm, and I hope that you're getting some nice information out of it. And I'm also looking forward to the discussions afterwards. Yeah. So let's jump right into it. Just another brief information. Who is this guy? I'm Stefan. I've been working in the railway business since 2016. And if you were here now, and if the weather would be a little bit better, you would have this view. So I'm located in lovely, beautiful Western Austria, where Rombach Sursa are headquartered. I have some assumptions for today. I guess you guys are here because you are interested in state-of-the-art developments for railway infrastructure construction. You are looking for safe and proven solutions, and you might, and Andy, you already confirmed that you might be interested in constructing or reconstructing faster and better. Because I don't get any feedback from the screens, and there is no other option than just saying the assumptions are correct. I'm going to operate based on that. And my goal is actually to give you a quick overview about the IVE Slab track, also to connect with you so you know who to call if you have any more questions that come up later, or if there's any kind of topics regarding this today's presentation that you want to discuss at a later point. And of course, I'm also really looking forward to exchanging knowledge and receiving valuable feedback. Just two brief slides about the Rombach Sursa Group. So the Rombach Sursa Group is active worldwide in construction, reconstruction, and maintenance of railway infrastructure. Last business year, we had around 700 million euros revenue and about 3,000 employees. And we actually operate quite a big number of rail-bound vehicles, also in the UK, actually. Where are we located? Headquartered in Austria. We are active in 9 countries with 100 branches, spanning from the US over to Australia. And sometimes we also do projects in various other countries. But for you, it's also important that we have a base in the UK. We have 2 offices, one in Wigan and one in Doncaster. So, typical challenges that people in the railway business, in the infrastructure currently encounter. Clients are running more trains, and consulting engineers have to plan carefully to ensure a quick return to operations, says a certain James Cooper. Or this year, Sophie Bennett, track engineer. She doesn't have time for maintenance, but stuff keeps breaking. It's kind of a nightmare. She needs a reliable and safe track. Don't worry, I didn't violate any GDPR regulations. The profile pictures and the names of these people are AI generated. That's nowadays easily possible. But they highlight some of the issues that we encounter every day when we talk to our clients, be it locally or internationally. Yeah. So this is some of the driving force behind what we actually do, and that kind of sets the stage also for our slab track system. Talking about slab track, Andy, you mentioned that already half a century ago you were part of, or you were involved with first installations of slab track in the UK. So slab track isn't new per se. I mean, it's a lot newer than the ballasted track, yeah. And also, I think in slab track there is still quite a lot of innovation going on. There's 6 classic types of slab track or categories. The monolithic ones, you might know the radar type, yeah. Embedded boots, there is one of the systems that's really well known is the low vibration track. Continually supported slab, this is where the IVES, our own system, falls into. Prefabricated slabs, for example, the POR SDA that you might be familiar with. Direct fastenings, there's a ton of those. For example, the DFS 300, or embedded rail systems, for example, from Edilon and numerous other manufacturers. So this has to, what we are actually focusing on today is a continually supported slab track system. Yeah, and I'm going to get into detail what this means. Before I go there, I want to highlight a little bit the experience of the Romberg-Sursa group when it comes to slab track. So we may be the only group of companies that has been continually building slab track for around 25 years, yeah, starting in the year 2000. And this is just a selection of projects, and there's many more. And we are, of course, currently also building slab track. One of the latest ones, latest really big project was the Koralm Tunnel. This is actually the one mentioned down here in Austria, which is 33 kilometers of tunnel, and it's two tunnels, so it's 66 kilometers of track, and that was executed with POR, for example. Yeah, you can see here the main systems that are, let's say, used especially all over Europe are the three mentioned before: radar, LVT, POR. Yeah, and so Romberg-Sursa has extensive experience in building all of these. But now let's jump over to the Ives slab track. As a colleague with a lot of experience recently put it, he talked about the Zierenberg tunnel. This was a project executed in 2018. He said it's as easy as constructing with Lego. And why he said that, we are going to talk about that right now. So adhering to the Lego reference inspired me to make up a really easy formula. So our slab track actually consists of a base layer, yeah, that you combine with prefabricated blocks and a fastening system. And what you get is a fast to build, reliable slab track. How fast can it be? Well, we are using fast curing materials like asphalt as a base layer, and different types of grouts for the fastening system, because it's a direct fixation fastener. And so we are talking about curing times in the range of 12 to 24 hours when it comes to the asphalt. And depending on what type of grout we use, for example, if it's an epoxy, it's really fast curing. If it's cementitious, it takes a bit longer. And this makes for a really fast to install system. But it's kind of that easy, but of course there's a few more bits and pieces to take into account. But I really like this analogy because it's it's easy. Everybody understands it, and it hopefully also sticks to people's minds. So, what are the actual building blocks of the system? Going from the top to the bottom. Well, of course, we need a rail. This is nothing particular about our system. Then we have the direct fixation fastener. It's a DFF 300 RS. This was co-developed with Vossloh, between Vossloh and Romberg-Sursa. Then we have here highlighted in orange in the 3D animated picture, we have the grout for the fastening system, and also for the dowel. Yeah, we have a shear dowel that I'm going to talk about a little bit later. We have the precast Ives blocks as such, and yeah, shear dowel also depicted here. That's for actually transmitting lateral and longitudinal forces into the ground. And we have a base layer here, the number 6. And so we can say that, yeah, okay, the rail is not specific to our system. We have like 6 main components or building blocks of our system. We tried to, stemming from our vast experience building all types of slab tracks, we tried to combine the best of both worlds, so to say, because there is the bottom-up approach where you are really fast installation. you have precast elements. You can still correct stuff. It's not, let's say, set in stone, and you can easily replace components. Examples are ATD and G-Track. Those are systems developed by Rail One, German systems. And there's the top-down approach that everybody knows. You get really high accuracy because the last step is actually the casting in, so you can really set your geometry really well. But this comes with the downside. There's no corrections after casting, or, well, just with shims. Replacement is really challenging because to take monolithic systems out of a tunnel or even out of an open track is a challenge. You have big heavy slabs if we talk about something like pour system, and you have quite complicated in situ concrete logistics and curing time. Examples are the before mentioned radar system, the LVT, the pour SDA. So we kind of took these two approaches and combined them. And I'm going to show you how we do that by going through the whole construction process, starting with the production of the precast blocks. So the precast blocks, you can imagine, they can be manufactured in sleeper manufacturing plants or any facility that can actually deal with precast concrete. They can be stressed or slack reinforced, depending on where they are used. For example, in Germany, we use pre-stressed concrete blocks. In other countries, such as even in the UK or Australia, we have used slack reinforced. Just from the forces and from the calculations, this is totally fine. And I will show you also that in reality it works. So this is how this can look like, different forms of production. Also long line production is possible. In this case, it was instant demolding plant. So then if we go to the construction site, either in a tunnel or out in the open track, here we have pictures. The right-hand picture is from Estropy Tunnel in Melton in the RIDC in the UK. And the other one is from Branxton Weybridge in New South Wales in Australia. There we just use like regular wheel pavers from road construction. This is a technology available worldwide. And you pave the tunnel floor or the tunnel invert, or you pave on the open track. And that's also where you build your super elevation, because our blocks are always the same height. We don't have like blocks that have different, let's say, left hand and right hand block height in order to do the super elevation. We always have the same blocks, and they are put on the asphalt, and that's how you actually create super elevation in there. Then I talked about it shortly before, the shear dowel. The shear dowel transmits forces in longitudinal direction and lateral direction into the subsoil or into the ground, into the base layer. And it's actually a steel pipe, a very rigid steel pipe that is put into or installed into the base, and that transmits these forces. It looks a bit like this. I have one here. If you quickly check out on the video, it's like 210 millimeter long and looks like this. There's it's just a steel pipe, high grade steel. And this is what we use for the shear dowel. You can see here how it's installed. And if you wonder what we have here, the foam part around the dowel and inside, that's the lost formwork that we need, because we are also using a grout to actually put the shear dowel and the block together to make them like a unit. This is what it looks like in the cross section, and here you can see the construction detail. So these are only necessary depending on the routing, which it means, for example, inside of a tunnel, you need very few of them, because there you don't have the temperature forces from the rails. At a tunnel portal, you need more of them, and out in the open track, the general guideline is to use one dowel on every third element. So if you have 3 elements, like the first and the last one will be doweled, and then the center one is not doweled. Yeah. All right. So what's the next step? Once we have the dowels installed, when they are necessary, the blocks are placed. This is how it looks. Our blocks are designed in a way that you can go over them with rubber tired vehicles. So you can actually use them for construction site logistics during construction time. Yeah. So they're stable enough, they're totally flat, and so you can actually drive on them, walk on them, and it enables you to have logistics also not just from the other side of the tunnel if we are in a tunnel. It also enables you to do that from the, let's say, backside, yeah, coming from where you are originally started. Sorry. So after the blocks are installed, the fasteners are placed. I already talked about it before. It's a direct fastening system. So in the beginning, you just place it there, and then you have to set up a track panel by lifting the rails into place and assembling the track panel. Here we see some picture from Bruchwald Tunnel that's in Switzerland. There we installed 1.6 kilometers of the IVE system. And what you can see here as well, this steel part, this is our track adjustment system. So this system is needed because, as you can imagine, we have two lines of rails, and we have fastening systems attached to them. So the gauge is not yet fixed, and the overall position is not yet fixed. Yeah, this is what you need a track adjustment system for. And when the track is adjusted, then you actually need to put a formwork around each and every one of these fasteners in order to be able to fill in the grout and fix it in the final position. First, before we do that, I'm going to show another slide where we can see a little bit better how the track adjustment system looks. So this one was especially developed by Romberg Sursa. It can be used for the IVE system, but it can also be used for other systems. So we have also used it for the radar system or for LVT systems. All of the systems that don't have a spindle already in place. If we install the POR SDA, as you might know, the POR system already has a place where the spindles go and is moved like that. But LVT and IVEs need a system like that, and it took us quite a while to work out a neat system that works really well. And this one has now been being used by a lot of projects recently, for example, in the refurbishment of the Gotthard base tunnel. So enough about that. You can imagine the track panel is now put into place. The geometry is aligned. We have a surveyor going through checking that everything is correct, that it's in the position that it should be. And then, as mentioned before, the formwork is placed, and then the fastening system is grouted. So the fastening system you can see here, like a schematic picture. We have these channels where you can actually fill the grout in, yeah, and the grout fills all the voids underneath and creates a neat looking solution where this is fixed in place and stays that way. The fastening system itself, you can see here on the right hand side, we have here some shims in there. We have an elastic base plate. This is the steel base plate, a rail pad, and the rail. This system was co-developed between Romberg Sursa and Voslao Fastening Systems. And on the next slide, I'm going to show you what it looks like when we actually do the grouting. So here we can see an explosion drawing going back into place. And now you will see how the fastening system is inserted in the block. The rail is placed, the clips are actually fixed, and then the whole system is lifted. So now we don't see any kind of track adjustment system here, but you have to actually imagine that. And in the end, like I said, formwork is put around, and then you can see now the grouting process. And this fills out all the voids underneath. It fixes the dowels in place, and it holds the whole system stable in place. And like mentioned in the beginning, you can use cementitious grout or an epoxy grout. It really depends on the construction requirements, also on time. Yeah, can also depend on cost. We have done both already, cementitious and epoxy. Both of them work. Okay, that was in the super elevation, but it's the same. So I've shown already pictures from inside of a tunnel and on embankment. So there's different cross-section designs available. IVES has been already installed both in the open track and in tunnels. Up until now, it has been installed more in tunnels than outside, yeah, but it's not limited to one or the other. This is an example of a typical cross-section now with all the details around it. For example, German railways, they require us to fill the sides left and right of the track with gravel, yeah, with ballast. This is just in order to protect the asphalt layer in case of a fire, for example. There is no other reason to have ballast here. Also, even if we are going on a straight track, we have an inclination of 0.7% in the asphalt, because we want this to be able to drain to the side. Yeah. All right. Now you might say, okay, great design, but does it work in real life? Yes, it does, and we have some examples to prove that. We have some nice references also from the UK. So one of them you can see here. It was the New Bailey Street in Manchester. You can see the IVES here, and you might ask, okay, that looks differently than what I saw before. Yes, because in this case, we did a special design with longitudinal IVES. So the system is quite adaptable, I would say, and also we are open to adaptations when it makes sense. And this was completed in 2017. It's only a short stretch, but still a nice reference from the UK. And the next one is Liverpool Street Station. This was done in 2021. It's around 300-meter stretch. If you are ever in London at Liverpool Street Station, you can look at that firsthand. But please don't go down to the track. Just look at it from the side, from the safe space. And then another one that we did in the UK was a quarry in Somerset that was done around 2 years ago. Internationally, one of the references I really like is the one in Branxton Weybridge. It was installed in 2017, and because it's a heavily loaded coal line, it has already endured 800 MGT. Sorry, there was a typo. 800 MGT. And if we compare that to like equivalent operating times in a European track, it's about 40 years of time in track, because a typical loading scenario in a European mainline track is 20 MGT per year. I'm curious also to hear what you think about that. What's like an average tonnage in the UK? But generally, these high loads really help us to, let's say, do like a pressure test or like a stress test on the system in quite short time, because the 7 years between 2017 and now are way nicer to in terms of a time to wait than waiting 40 years. So you might agree, we are not really patient with these things. But yeah, so this is still working fine, and the operator ARTC is happy with this. The next reference or example from the real life application is the Zierenberg tunnel. This is a tunnel that we equipped in 2018 for the operational testing phase that you need for approval in Germany. And yeah, this is perfectly fine. We did a tracking inspection last November, and everything was found to be in perfect order. So now we are just waiting for the red tape to be cut, meaning that we will get the general approval for the network of DB. Mentioning that, I also have to say that in the UK, we are working on the product acceptance with Network Rail for the ICE system, because we until now it was always installed on a project approval base, but in the future we want to make it easier for everyone, cut the red tape, and have a general product acceptance. And we already have a sponsor, and we are quite well informed about the process. So we are optimistic to be able to have the product acceptance, maybe even by end of this year. Another one that I showed before is the one in Switzerland, 1.6 kilometers, installed also in 2018. Track inspection this year. I was there myself, showed that everything is working well and the client is happy. So overall, there's a little list of references. We have installed around about 5 kilometers of IVE Slab track. And of course, we are looking forward to further projects. There's a few in the pipeline, some mentioned here, some not mentioned here. And of course, we would be very happy to also do some more projects in the UK. Last but not least, I want to quickly talk about getting better. This is a quote that I found that's attributed to Oliver Cromwell. I don't know if he ever said it, but I like it because he who stops being better stops being good. And that kind of also drives Romberg Sursa to get better on a regular basis. So we continue the design improvements, for example, by reducing the asphalt layer. Here we had to test the lateral track resistance, pushing the blocks from the side, measuring how well they hold. There was a dowel installed in all of these 3 blocks. We did this little mock-up construction, and then we checked the lateral track resistance. We don't have the official report yet, but I can tell you the values were really high. Also in the process, we improve. This is a picture from the humble beginnings of the grouting process. You have to start somewhere. Nowadays, we have a half-automated mixing and grouting unit. And this is a more state-of-the-art way of installing this. It's also more controlled and gives you safety that it will work and that everything is documented. Also, for the other process steps, we have plans to improve. We have a drilling robot that's actually already used, but not yet for the core drilling for the IVEs. We have a gantry crane that we can also use to place not only pour slabs like here, but also our blocks. And last but not least, we developed our own track adjustment robot called ROMAT. This has been successfully in use in Germany in a stretch where we installed several kilometers of radar system. And I just met a guy from Deutsche Bahn at Inotrans last week, and he said they were really happy about it. The accuracy was up to, or the accuracy that they achieved was 0.3 millimeters deviation. And I just heard a weird sound, but I think I'm still in the call. All right, I'm almost done with my slides. What is the added value of the ICE Slab track? You can have short track possessions, so high availability, high precision through prefabrication and innovative fastening, safety through proven long-term performance, and also, last but not least, easy replacement and dismantling because it's a modular system. Think of the Lego. There is a documentation, a short one on YouTube, so the link can be shared with you afterwards if we share the presentation as a handout. And that's about it. That's the end of my presentation, and I'm looking forward now to answering questions. And of course, if you want to get in touch via LinkedIn, please feel free. You can find me with my name. Thank you.
Stefan, thank you very much, and congratulations on having Welsh in your thank you. So it's quite rare to see it.
Yeah, especially for this presentation.
Yeah. Okay, I'm going to use chairman's privilege and ask a question myself. If you've got your base layer in, how long does it take from then till being able to run trains for, you know, say 100 meters?
Yeah. So the answer, like many times in engineering, is it depends. So what we did, for example, let me share some examples from actual projects that we executed. So in Australia, because this coal line is not to be interrupted, yeah, they did the asphalt layer and then put sleepers on top again, like regular ballasted track sleepers, just without the ballast, and had the trains run over that until the next possession where they were allowed to actually place the blocks, you know. So in this case, it would be, if we are only talking about the asphalt layer, then it's in the range of 12 hours plus putting like a, let's say, temporary track on top. Yeah.
And the whole system?
Okay, about the whole system, if we would not split it that way, if we would say we pave, we wait for the pavement to be, let's say, cured in order to be able to place the blocks, and then place the fasteners and the rails, then we can still use that as a temporary permanent way. Temporary permanent way doesn't work. A temporary track by adding gauge holders and placing the whole the rail on wooden beams, and then we are talking about, let's say, something like 2 shifts. Yeah, so 2 shifts of 8 hours, maybe like 16 hours or something.
Okay, thank you.
Yeah. Okay.
Safari asked, what is the construction depth? I presume that's the construction depth of the actual elements, the beams.
Probably it's easiest to jump to the cross section, because many times, I mean, if we talk about construction depth, then people are, well, depends. Okay, so the blocks themselves are 250 mil, 255, because there is a geotextile on the bottom. Yeah, you can see that around right here. The fastening system is around 267, but this is with UIC 60 rail. Yeah, and then it depends which thickness of asphalt we are using. But if we just talk about the blocks, it's 255 plus the fastening system. Okay.
Thank you very much. I hope that's okay for you, Safari. Yu Heng Li asks, is there any other binding with the asphalt layer other than the shear connector every 3 blocks?
No, they are just placed there. They weigh almost a ton, yeah, 950 kilos. So there is also some friction going on, of course. But other than the shear connector, there's no other connection to the bottom. And that's why, for example, refurbishment after an accident or at the end of lifetime to get the blocks out is really easy.
All right, thank you. Chris Deacon, do you want to ask your question?
Can you hear me?
Yep.
Yeah, sorry about that. Just I'm out in Singapore drying a small child. It's a bit late at night here, but it's a great presentation, Stefan. Thank you for that. Yeah, it was just about noise attenuation. I think that there's a second question by someone else in the chat, similar. How do you sort of advent for any noise attenuation, inserting of dampening systems or different base plates? That links to the other person's question, I think, as well.
Yeah, that makes total sense. Of course, this is something that we are looking at. We do not have a functioning or let's fully developed mass spring system yet, but we are currently working on it. Yeah, because this requirement comes in many markets. Because if you are somewhere in a tunnel underneath where people work or live or sleep or have babies, such as yourself, then you want to reduce vibrations. So what we are currently looking at is placing an elastic layer underneath the blocks. Placing an elastic layer directly underneath, no problem. Placing an elastic layer directly underneath the blocks, and up until now, the simulations and calculations that we did with that give us an eigenfrequency of about 18 to 22 hertz. Yeah, but we will of course have to verify that with field testing. I'm optimistic that by first quarter of next year, we will at least have like real life tests about with the mass spring system version of IVES. Is that okay?
Excellent. Yeah, that's great. Thanks, Stefan. We're always
you're
looking
welcome.
for different systems and different providers, and we do have a lot of underground board tunnel that go past sensitive structures and sensitive receivers. So but it's always tricky because we have such a tight diameter for the Singapore MRT here.
Yeah.
We're always looking at different methods, and we were just down in Perth doing some work down there recently. But yeah, I think it'd be good to catch up offline at some point.
Please.
I'll leave it there because the child's going to start losing her mind. But yeah, thank you very much, Stefan.
You're welcome. Cheers.
Yvette Kruger, you also talk about noise and vibration, and you have another question. Would you like to come in and ask your question?
Yeah, just really simple. I just wanted to know whether other systems are compatible.
You mean like
combining
it? Yeah. So if it's a direct fastener, it should work with our system. I mean, we would always have to look at the dimensions, etc. But generally, I mean, the fastening system that we are using now, let's say, is the preferred and approved one because we were part of the development team. So this was a co-development, like I mentioned, with Voslo. But if in other places, for example, where they prefer Pandroll fasteners or other manufacturers, then we would just have to look at an existing direct fastener from Pandroll, for example, and combine it. But we haven't done it yet. Yeah.
Okay, and then just a kind of a second part of that question, the fastenings that you have developed now, do they have a range of stiffness pads that you can use?
The standard pad is 22.5 kilonewtons, but especially, for example, for the mass spring system that I talked about before, there we would go with a lot stiffer pad because you don't want two different elasticities in your system, because then you get let's say negative, like a resonance in a frequency that you don't want. So from Voslo point of view, last time I spoke to them, we can be in the range, I think, from 22.5 up to 100 kilonewtons can be the range of the base plate pad. Yeah.
That's brilliant. Thank you, Stefan. Dankeschön.
You're welcome. Yeah, gerne.
Thank you very much, Vivek. Chris Fleming, an interesting question from you. Would you like to pose it?
I was wondering if you supply custom width units to accommodate S&C, so switches and crossings.
Until now, we haven't done that yet. There's designs for, let's say, putting those blocks together smartly. Again, referring to the Lego idea, but we haven't yet built S&Cs with ice blocks. Yeah. It might be that before if we would need that quickly, then we would probably go with a different system, for example, like a radar switch or radar crossing, because it's already existing, it works, we know how to deal with it, and we wouldn't have to go and further develop. But in the long run, of course, we want to have the IVES system also available with the blocks for the S&Cs. Yeah. But currently, we would help ourselves with a radar crossing. Yeah.
Yep. Okay. Thank you.
You're welcome.
Then no, it was the final questions. Another one just come in. William Rothery, your question, please.
Or rather in the USA, I'm interested just on the long-term maintenance of this system because it's obviously not a continuous slab. I was wondering if there's any adjustment, should any settlement occur between the different parts, or whether the design should not have any settlement at all within it.
So in a perfect world, no settlement occurs, yeah, but we know it's not a perfect world for several reasons. So there's shims to be used. Just going to show them into the camera here. These shims made of polyamide, also reinforced with fibers, is the way to go for like a certain amount of settlement, yeah. So the total adjustment height of the fastening system, if you are interested, I can send you the data sheet of that.
Yeah, that'd be great.
Yeah, cool. So just maybe if you jotted down my email, or if I just jump to that one back again, then you could remind me after that presentation, and I'm just going to send it over to you. Yeah.
Sure thing. I'll drop my email in the chat.
Yeah, cool, perfect.
There is also a PWI LinkedIn discussion page that will be set up after the conference, after the call, when the conference is finished, so you can use that.
Yeah, yeah.
Right, thank you.
So that's one thing, and I might just add that in the track in Australia, there was some external factors that led to settlement in a section of, I think, 7 to 8 meters, quite severe settlement that was too much to do shaming. Yeah, and there we actually worked with these injections that lifted the whole track in this section, and we just recently did. So this was done like 2 months ago, roughly. And after that, the surveying showed that we are now back in the tolerance at time of construction. I think there's also companies that do that in UK. If I'm not mistaken, GeoBear, for example, like this type of injections can also be used if you have severe cases of settlement and when the shims are not sufficient.
Thanks.
Welcome.
Thank you. David Woods asks, is there a declaration of conformity for the IVES system at this stage?
Declaration of conformity would mean that it's an approved construction product according to European guidelines. As far as I know, I can say we don't have it. I'm not even sure if you can do that for this whole system. There I would have to check. Yeah, but I know that we don't have declaration of conformity when it comes to this, what is it called? These homologated European standards. But if this is required and if it's possible, then we would work on it. Yeah.
Okay. Thank you, Stefan. I think, yeah, it's David Woods. We are considering this on the transparent route programme for some of the tunnels, I believe. And one of the key things at the end of any project is to make sure that we've got one of these declarations of conformity that can lead to quite a tortuous process if it's not in place.
Yeah. Okay. And they are, just for me to understand, are they separate from any kind of product acceptance by network rail?
Yeah, it's not the same thing. So you can have product acceptance, but you might not have a declaration of conformity. Okay.
Yeah. Okay. I'm going to look into it, but it's good to know that this is something that we could prepare also in order to cut red tape during a project, right?
Brilliant. Thank you.
Mm-hmm.
There are the same question in slightly different ways from both Ranga and Paul Ebbert. Talks about transition arrangements between track forms or transition between ballasted and ballastless track. And I know this has been a real issue with London Underground in the portals on the Northern Line. I had to do a civils interview on that many years ago, so I'm very interested in that myself.
Yeah. So you just saw a window pop up. I'm going to show you very quickly another slide that was not in the presentation of before. Is this the good one? Let me check. So what we have done is, because we know that differential settlement always occurs when you change the track form, we have developed our own system called VTRAS, which is a transition module. Okay, I'm gonna show this here very quickly. So it's called VTRAS, Versatile Transition System. Yeah. What it does is, at the change from say slab track to ballasted track, we want to avoid this differential settlement that always occurs there. I'm quickly jumping down here. So what is this VTRAS system? It looks a bit like a ladder. Yeah, it's a metal construction. It's like a beam. a levered beam, and you actually attach it to the slab track side of things. Yeah, you need like a concrete element there that serves as a bearing, and the rest of it is just laying in the ballast. And it has elastic material on the top of this ladder here, depicted in blue. Yeah. So these are some elastic pads between the steel and the concrete sleeper. And underneath, you have something like a sleeper pad to prevent the ballast from crushing by the contact between steel and ballast. Okay. So this one is a solution that is kind of a plug and play solution that works really well to prevent differential settlements in these transition zones. And maybe you have heard of it, but maybe not. Also in the UK, we have installed quite a number of these units. Yeah, for example, the project Barking to Gospel Oak in 2016, we installed like 12 of these. Yeah. If anyone is in the call who knows about these projects in the UK, I'm also interested in getting feedback about them. Doesn't have to be now, can also be later. But yeah, so these units have been installed and they prevent differential settlements exactly in this place between slab track and ballasted track.
Thank you. Chris Fleming points out that this system was used on the Edinburgh-Glasgow improvement project at Winchburg Tunnel as well.
Oh, so, yeah, perfect.
Yeah.
Thank you.
Okay, Paul Waterhouse asks, what's the maximum super elevation that the system will take, the Ives system that is, and what is the steepest camp gradient that you can accommodate?
Highest super elevation I know by heart, it's 180 millimeters, because it was developed to be used also for high speed up to 300 kilometers an hour. Steepest camp gradient, I have to check. I don't know by heart. I'm sorry. I have to be so honest.
Okay, or again, one for the LinkedIn discussion afterwards.
Yeah.
Okay, I think we've gone through the questions that have come through on the chat. We've got about 5 or 6 minutes left. Does anybody have any other questions that they want to ask? If they could raise their hand, if so, please. Deathly hush. Stefan, I think you have answered everybody's questions absolutely magnificently. I'm very impressed at the range of questions that were put forward. Somebody's clapping on the screen as well.
Yes.
But a very wide range of questions, and you've answered them all brilliantly. Thank you very much indeed. And as I said, the discussion will carry on the PWI LinkedIn page if anybody wants to go any further then.
Yeah.
So I propose to wrap the session up at this point. Thank you again. Lots of people saying thank you on the chat group as well.
Thank
the
you.
next session will be a fortnight today on reinforcing rail earthworks in the face of climate change. So that promises to be another very interesting one, and I will join it if I can myself. I won't be chairing it. Stefan, thank you very much from everybody.
Thanks.
And thanks everyone for coming.